Welcome again to the virtual seminars in economic theory. Today we have Giacomo Lanzani, who's getting up early from to talk to us about nonlinear fixed points and stationarity economic applications. This is joint work with Simone Cerreia-Vioglio and Roberto Corrao. We're also lucky to have two panelists today, Agathe, Pernoud, and Sanjeev Goyal. Sanjeev is not here yet. He'll join us in approximately 15 minutes. That's been agreed. Also, I just want to remind you that next week, we're going to have Marina Alak from Yale, who's going to talk to us about agreeing to implement, which is joint work with Elliot Lipnowski and Doron Ravid. Also a reminder that we are recording and that the talk is supposed to last an hour with approximately 15 minutes for question and answers later on. Giacomo doesn't have his co-authors with him today, so if you have questions, just please unmute yourselves and ask. Okay? Giacomo, floor is yours.
Okay, thank you very much. Thank you for the invitation, and I'm very excited to have the opportunity to present my work at VSET. I'm a big fan of the initiative and sort of happy to present it for the first time. Let me introduce a little bit the motivation behind this project with Simone and Roberto. What we realize at some point is there is a common structure of a fixed point equation that show up prominently in many network settings. You should really think about a very broad range of applications that share a sort of solution of the economic model involved with networks, the same kind of equation. And they range from general equilibrium model in production network to model of financial network to equilibrium of games on network with complementarities, as well to long-run outcome on non-Bayesian opinion aggregation, and beyond the realm of models with a network component, there is also the same structure in the value of a Markov chain of a pair of relevant states. So the starting point for us was really realizing that there is this common structure among these models, and that at the same time, the network literature often impose simplifying assumptions that make this fixed point equation linear. Why they do so? Well, because in that case, we know everything about what's happening. It's a very sort of, it can be captured with a very simple formulation, and that I can spell out.
Recording in progress.
In a single slide. So the idea is that in all these models, when simplified to the linear environment, there is a set of nodes N that are connected to a stochastic matrix W. This stochastic matrix W is what's capturing the network, is telling for every agent for every node, what are the other nodes that are important for them. And the fact is stochastic means that every row is a probability measure. So basically it's telling you a normalized influence of the others on a particular node. And in all the previous model, what you get is in the linear case, the fixed point simplified to the following form. That is, on the left-hand side, x beta. X beta is the endogenous object for this model, what we want to solve for. And on the right, you have that x beta is equal to a convex combination of weight 1 minus beta x, 1 minus beta of x, that is a vector of exogenous parameters, plus beta, the fixed point itself, pre-multiplied by the stochastic matrix W. So to gain intuition, think about a beauty contest, a coordination game. So as the players have an endogenous action in equilibrium, that is x beta, that is a convex combination of their bliss point of what they would like to do, and that's captured by this vector x, with weight 1 minus beta. But at the same time, being a beauty contest, they also want to match what others do. So they have some importance of others that is captured by the matrix W, and this matrix W is pre-multiplying the vector x beta to capture the intensity of the desire to match the equilibrium behavior of the opponents. Now, As I said, in the linear case, we know everything about this problem because we know that the solution in terms of x beta is explicitly given by the infinite summation of the power of the matrix Wt multiplied by beta t. So this is a formula that oftentimes is called Bonacci's centrality of the problem. So the equilibrium behavior is a weighted average with the power of the matrix W capturing these weights of the exogenous Bliss point of the agent. And there is a particularly sharp and nice result when we take the limit as beta goes to 1. That in this model, as the interpretation of taking the limit as the coordination motives prevail. Also, when you want mostly to match the endogenous behavior of the other rather than your exogenous Bliss point. Because in that case, if the matrix W admits a unique left-Perron-Frobenius eigenvector, what you get is that the limit as beta goes to 1 of x beta is equal to a constant, and in particular to the inner product between gamma and x. So the product between this exogenous vector of Bliss point of the agent pre-multiply by gamma, that is the eigenvector centrality. Why this is nice? Because in this way you have a unique centrality measure that is telling you what are the agents that are more central in the network, who you should target if you want to increase the endogenous behavior of the agent, and sort of also the size of the effect of changing x on the equilibrium behavior x beta. So I think this is sort of very nice, and this has been used in all these network application as well, and sort of dynamic programming application that I mentioned at the end, but it has a main limitation. The main limitation is that in all these applications, non-linearities naturally arise. So it's not something that we are going to introduce in this paper. So people smarter than us in this literature already recognize the need for considering the nonlinear version of this fixed point. Why? Well, let's very quickly go over again the application that I was mentioned. So that is the fixed point that characterizes production network. But as soon as this production network that are using macro allow for endogenous network selection or non-Cobb-Douglas production function, the beautiful linearity of the previous equation that you had is lost. In financial networks, banks are literally required by regulation to use a robust loss assessment rather than evaluating their losses at expected value. And this is immediately introducing nonlinearities in the fixed point equation that characterize the equilibrium. In games on network with complementarities, if agents are allowed to choose their network, to choose their peers, or they have non-quadratic pair function, nonlinearity is immediately lost. If we look at non-Bayesian opinion aggregation model, we have that if you allow for opinion-dependent weights, in which I may weight Francesco a little bit more if it's more extreme or intermediate, linearity is immediately lost. And in the Markov problem, when the transition over state is partially controlled by the decision maker, so we go from the evaluation of a stream of utility to a Bellman or Shapley equation, then immediately linearity is lost. So what we are going to do in this paper? Well, in this paper, we provide a theorem today, well, two theorems today that characterize this nonlinear fixed point in the limit as beta goes to 1. This is as the great advantage of giving a formula for this fixed point and restoring the possibility to do comparative statics in terms of what are the more central agents in the network, who we should target to boost the equilibrium behavior, even in the nonlinear case, restoring this sort of insight that has been extensively used in the linear specification. Okay, so this is going to be the goal of the game, and the reason why I think is important, because having a formula for the equilibrium, so sort of a particular quantification of how the equilibrium behavior depends on the exogenous parameter of the model, will allow us to tell how a shock to one sector affected the GDP in production network. In financial network is going to tell us which kind of risk measure induce robustness of the evaluation of the banks of their exposure to the real economy. In games on network with complementarity, it tells us who to train to boost agents' payoff. Under non-Bayesian opinion aggregation, it tells us who to seed to maximize the long-run adoption of some behavior. And for Markov decision problem, it tells us what kind of preferences have the feature that as patient increases, patients mutes uncertainty and risk aversion. So in the paper, we go through all these applications and show why the theorem that we have sort of allow us to make this conclusion. I'm going to focus on two of them in today's presentation beyond the sort of general theorem. Okay, so this is a little bit the end of sort of this introduction in which I explain you where we are going. Now, in the next few slides, I'm going to give you the mathematical result about this kind of fixed that show up in the application that I mentioned, and then in the last part of the in the second half of the talk, I'm going to apply this result to two particular application that I decided to focus on today. Okay, so let's start with the kind of generalization of the linear fixed point that we are going to consider. So it's obviously hopeless to be able to characterize all nonlinear fixed points for arbitrary complex operators. So we have to strike a balance between having something that is sufficiently general to cover all the previously mentioned application, but at the same time that is sufficiently tractable to obtain the conclusion about what is the value of this fixed point. And the balance that we found is the following one. We are going to consider operators that have three properties. Let me first denote as E the vector which entries are all equal to 1. And the operators that we are going to consider are operators that have three properties. First of all, they are normalized. So if you give me a constant vector ke, so it's the constant vector at 1 multiplied by a fixed number k, what the operator is returning is ke itself. Okay, constant vectors are mapped into themselves. Monotonicity is the usual monotonicity. If you have larger input, you return larger output. And then you have translation invariance. If you shift by ke by a constant vector the entries of the input, the entries of the output are shifted by the same amount. Now, with this free property, you should really think of T as the counterpart of the stochastic matrix that we had before, of generalized averages. So a property of average is that if you have a constant vector, the average of that constant vector is that constant itself. That's normalization. Averages are monotone, so the larger the inputs, the larger is the average. And some of the average, so this is a restriction, are translation invariant. So that's sort of an additional property that is capturing a particular subset of generalized averages. And if you want to have an example to keep in mind, sort of to fix ideas, think about the median. So the median is one operator that satisfies these properties. A minimum over a set of possible matrices, so not the matrix W applied to X, but rather a minimum or a maximum over a set of matrices applied to X, or many of the measures that are used in finance, like expected shortfall, value at risk, all of them are nonlinear but satisfy this free assumption. And in particular, in this case, the fixed point equation that we are going to consider is exactly the counterpart of what we had before in the linear case, but now with the stochastic matrix W replaced by the operator T. In particular, the fixed point equation is that x beta is equal to the convex combination with weight 1 minus beta of x plus beta, the operator T, this generalized average, applied to the fixed point itself. So why we study this? Because all the nonlinear version of the linear models that I've mentioned before, that have been considered in the literature, have a fixed point equation that has of these four. So it's nonlinear, but now T T is an operator with the three properties that I've mentioned. Now, the problem is that you don't have an immediate way to compute the solution for this fixed point and to be able to say who are the agents that are, or the nodes that are more central in determining x beta as a function of the operator T. That is what we want to do, sort of gain an understanding about who are the more central agents when sort of the interaction among them is captured by possibly this nonlinear operator. Now, we want to solve then for the fixed point x beta. Let me preview that the existence and the uniqueness of this fixed point x beta is a trivial matter, okay? Because what we have on the right-hand side, the combination of the operator T and the operation of mixing with weight 1 minus beta with x is a contraction. Okay, so it's immediate by Banach contraction principle that there exists a unique fixed point x beta for every pair of x and beta. But what we don't know is the value of this fixed point, and in particular, how sort of is determined as a function of the input of the agent and who are the most central agent in determining that outcome. And what we are interested in particular is the value of x beta in the case of vanishing dependence on the fundamental, in the case of the limit as beta goes to 1 of x beta. So what we had in the previous linear case is sort of this result about eigenvector centrality being the key determinant of who are the most central agent. We want a result like that, but for this nonlinear operator that are sufficiently general to cover all the application in this line. Okay. Now,
wait, Giacomo, can you give us a little bit more motivation as to why you're looking at that limit specifically? Is it giving you like a lot of tractability, or is it like economically we're interested in that limit?
It's a mix. So many of these applications have studied this limit. So beauty contest, in a sense, is literally the case in which we only care about matching the others. It's in the dynamic programming case, this is a patience. And the classical exercise that is done in this literature is looking at the limit as patient goes to 1. But there are exceptions. For example, in the production network literature, beta corresponds to the labor share, that one can claim is declining over time and becoming smaller, but is never exactly equal to 1. For that case, it sort of is also giving a lot of tractability. But exactly because for some of the application, for most notably the general production network one is a restrictive, what we supplement the result about the limit bit as beta goes to 1 of x beta with rate of convergence result. So we show that the limit sort of approximate already pretty well the behavior of the fixed point for beta high by not equal to 1. And moreover, but this is not really what we like to focus about on the paper, we have a counterpart of the Banach centrality formula for a few cases for beta away from 1, but that is more involved. I would say that sort of the focus of the paper is that limit that in many applications is justified, and for other applications give us tractability and is not distant from what would be the equilibrium, what it would be the sort of fixed point for beta high, but not equal to 1.
Thanks.
Okay, good. Now, that's a very good question because sort of this is the object that we're going to study from now onwards. So it's important to know why we care about that one in particular. Now, the first step is to realize that we need something like the previous condition that there exists a unique left performance eigenvector. Okay, so for the linear case, that simplification that we achieved in the limit was obtained under the condition of existing a unique left performance eigenvector. That basically is a condition of connectedness of the stochastic matrix. For example, a sufficient condition is that the stochastic matrix W is irreducible. You need something less, but let's think of that as sort of the content of that requirement. Now we need something like this. Also in the nonlinear case, we need an idea of the operator T being connected. And so something that we can do, and we do in the paper, is to extract a network from the operator itself. In particular, we have the advantage that given our property, the operator T is Lipschitz. So by Rademacher theorem is almost everywhere differentiable. So it's not in general differentiable, and that's important because in many applications there are natural non-differentiability that comes from endogenous network selection, but almost everywhere differentiable comes for free. Now let me denote as D the set with null complement where T is differentiable. So the set where this is differentiable. And with this, we can define an agency matrix, a network associated with the operator. And in particular, I'm going to say that node I is connected with node J if and only if I can find an epsilon ij strictly larger than 0, such that the response of entry I in changes of entry j of the operator is bounded away from 0 with this constant epsilon ij. So this means that I always care about what is happening to j, what j is doing. And we are going to say that T is regular if the network that has been constructed in this way is strongly connected. Okay? So that is going to be our counterpart of the existence of a unique left pair on Frobenius eigenvector. It's the condition of connectedness that we are going to assume. The paper considers much weaker notion of connectedness, but this is the one that can be sort of stated more compactly. So you elicit a network, and we are going to assume in the result, in the theoretical result, that the network is strongly connected, the network that we have obtained like this. And with this, I'm already in the position of giving you the first theorem of the paper. The first theorem of the paper is going to consider the case in which the operator T is continuously differentiable. As I said before, these operators in the application that we are considering oftentimes are not differentiable. But there is a large class of them that is differentiable. So we first give you a theorem that covers the differentiable case. And then after that, I come back to a more alternative theorem that covers basically all the other cases that are not differentiable. And if T is continuously differentiable, let me denote as JT0 the Jacobian of the operator evaluated at 0. 0 here is the vector of all entries equal to 0. Now, the properties of T that we have considered from the beginning, normalization, monotonicity, and translation invariant, readily implies that the Jacobian of the operator evaluated at 0 is a stochastic matrix. Okay? So, we have the Jacobian is a stochastic matrix. And the result is the following. It is continuously differentiable and regular, so there is disconnectedness. Then, the limit fixed point of the operator as a formula that basically mimics very much what we know from the linear case. So the insight of this theorem is going to be that the differentiable case behaves much like the linear case. That is going to be very different from what happens under non-differentiability. Why I'm saying that this behaves very much the same? Because the limit is again equal to the product of x, the exogenous vector of parameters, with gamma t. And what is gamma t? Well, gamma t is again a eigenvector centrality, but the eigenvector centrality no longer of the stochastic matrix W that characterizes the linear case, but of the Jacobian of the operator evaluated as 0. So what we have in the differentiable nonlinear case is that there is still the insight that in the limit there is a unique, well-defined centrality measure that describes who are the most important agents. This centrality measure is again eigenvector centrality, but it's telling you where to go to compute this eigenvector centrality. Go look at the Jacobian of the operator at 0. That's the right point to look at the centrality. So this is extremely simplifying the computation of the fixed point under low anchor dependence, so with beta approximately equal to 1. And given that I have some time, I'm going to give a little bit of proof sketch of this result. It's the only proof sketch that I'm going to do today. It's not the way in which it's done in the paper, because in the paper everything is derived as sort of the consequence of a meta theorem, but it's the sort of self-contained proof that I can explain in a couple of slides. So what you can do for the differentiable case is to do the following. Take a converging subsequence. So you have a converging subsequent x beta t that you know exists because the property of t make it a generalized average, and so in particular implies that x beta always lies between the minimal and the maximal entry of x, the box composed by the minimal and maximal entry of x. So we have a converging subsequence because we have a subsequence in a compact, we have a sequence on a compact set. Now, the fact that the operator is regular, so this connectedness property, implies that only constant can be fixed point of t. So this is the strength of the regularity assumption, that the only fixed point of t are constant vectors. But by continuity of t, we need that this limit of the converging subsequent must be a fixed point of t itself. Well, why? Because we are looking at this fixed point. We let beta goes to 1. On the left, you get x star. On the right, this first term is disappearing. The second term is becoming t of x star. So since t is continuous, you need that x star is a fixed point of t. So we know that this limit of the converging subsequent must be a constant vector. Okay? So good, we know that it's a constant vector. Now, here is sort of the place where I'm cheating a bit. That's why it's only a proof sketch. By the mean value theorem, but here you have to be careful because we are considering a vector valued function. So the mean value theorem, you don't really need to apply the standard mean value theorem. What you get is that you can replicate the difference between the operator evaluated at tx beta and t key e as the product of the Jacobian of the operator evaluated at some point that lies between the two of them, multiplied by x beta minus ke. So at this point, you get that tke simplifies away with the ke, and that t of x beta is equal to the Jacobian of the operator t evaluated at x at beta t. And therefore, you're basically at the level of a linear case. You have that x beta t is equal 1 minus beta t x plus beta t, the Jacobian evaluated at this point that you don't know. Okay, that's the problem. You don't know what this point is. Multiply by x beta t. So here, for any given beta t, I'm back to the linear world. So this is the linear fixed point with the Jacobian of the operator replacing the stochastic matrix of the linear world. But we don't know what is the point in which this Jacobian has to be computed. That's the difficulty. But you can still sort of perform the inversion and get x beta t as the infinite summation of the power of the matrix. That's something that we can still do with the caveat that we don't know what is the Jacobian. And I'm getting this last step on top of this slide. And then what you do is to pre-multiply everything by the Jacobian gamma t of the operator, of the Jacobian of, the Lepperon Frobenius eigenvector of the Jacobian of the operator evaluated at x beta t. So you multiply everything for the Jacobian. On the left-hand side, you obtain this unknown fixed point multiplied by the Jacobian, again, by the eigenvector centrality. Again, this eigenvector centrality, you don't know what it is because you don't know what this Jacobian is, being equal to gamma tx. Why? Well, because here on top, if you pre-multiply everything for the eigenvector centrality, you bring inside the summation is literally the eigenvector centrality of the matrix. So the product of the eigenvector centrality times the matrix is returning the eigenvector centrality itself. So you get gamma times x. So that's what you get for every t, that gamma t x beta t is equal to gamma t times x. Now you take the limit as t goes to infinity, and you use the property that the eigenvector centrality is continuous in the matrix where it is computed, if the matrix is regular, and that continuous differentiability is telling you that the Jacobian the Jacobian is getting closer and closer to the Jacobian at the constant Ke, to obtain that K is equal to gamma t times x equal to gamma t, x star equal to gamma tx. So you have obtained that for every converging subsequence, the limit is equal to gamma t times x. Okay, so, but if this holds for every converging subsequence, it also holds for the initial sequence. So you have proved that the limit fixed point must be equal to the Jacobian of the operator t evaluated at x. Sorry, something that I didn't mention is I'm using the fact that the Jacobian of the operator Ke, this constant that you don't know, is equal to the Jacobian of the operator at 0. This is a property that's following from translation invariance that we are using, because otherwise here I would have the Jacobian of the operator Ke that is a point that I'm computing, so I don't know. But the advantage is that it's a constant. I know this from regularity, and translation invariance is implying that the Jacobian at the constant is equal to the Jacobian at 0, so I can pick that particular point. So very much sort of confirmatory result, in which is telling us that eigenvector centrality is still the relevant measurement, but also telling us where to go to compute that eigenvector centrality. And I want to contrast this with what we are going to obtain as the next result. A next result that we develop, because
wait, sorry, before you, okay, can I interrupt you? So can you go back to the previous slide? So you get, I'm trying to like find intuition as to why the Jacobian at a constant vector pops up. Is the intuition that in the limit, the x beta I is going to converge to something constant? Okay.
Very good. Yes, that's the strength. So that's the strength. So regularity is giving you that this is converging to a constant.
Okay.
And that's, so in the proof, that is what is happening. So the fact that every converging subsequent is converging to a constant vector. But you can already sort of make a guess, if you want, starting from the result itself, because since it's converging to be a constant vector independent of I, where sort of the centrality measure is the same for everyone. So that's a sort of the difference between Bonacci centrality, in which you have a centrality that depends, you have your own Bonacci centrality, I have my own Bonacci centrality, to eigenvector centrality, in which the centrality measure is the same for everyone. So we are converging to a constant behavior, and that's the intuitive reason why the Jacobian at the constant is going to be important. Then at 0, because we need to compute it, and we cannot assume that we know the constant we are converging to. Okay?
Okay, thanks.
But that's regularity. And sort of the most exciting new result that we are developing is exactly at the moment relaxing this regularity condition to be able to obtain the results also when you don't converge to consensus. But for what I have said today, that's the reason. Okay? So there are a lot of differentiable models. For example, the very influential class of nested CS production function that has been proposed by Baki and Fari are differentiable. Models of confirmatory bias in nonlinear opinion aggregation are differentiable. Literally, smooth risk measures that are used in finance are called smooth because they are differentiable. But there are many non-differentiable cases at the same time. Most prominently, the one that involve an endogenous network choice, in which T of X is basically, I first choose a network, a set of possible connection, and then I use that stochastic matrix to evaluate the vector X. These are inherently non-differentiable and are exactly the kind of operator for which we develop our second theorem. A second theorem that is going to cover the concave case, the case in which the operator is concave. And when T is concave, let us first denote its super differential at X as partial T of X. Okay, so it's concave operator, so it's always non-empty. Good. We also have the property that if T is concave and regular, first of all, each element of the super differential is itself a stochastic matrix. So the elements of the super differential are networks, if you want, stochastic matrices. And moreover, regularity implies that each of the elements of the super differential at 0 admits a unique left Perron Frobenius eigenvector gamma. So it's connected itself. And therefore, denote as gamma partial T of 0 the set of eigenvector centrality that are associated to the stochastic matrix W that belong to the superdifferential of the operator evaluated at 0. Okay, so these are a set of eigenvector centrality associated to the matrix W that lies in the superdifferential of the operator at 0. And then the result for concave operator read as follows. Let be T concave and regular. We are going to get that the limit is again constant. This is again the strength of regularity. But now with the intuition for the linear case carries on only in a very limited sense. In the sense that what we are going to have as the limit is again the product of the exogenous vector x times an eigenvector centrality. So there is still the core message that eigenvector centrality is the right measure of centrality for this kind of models. But now you don't have a unique eigenvector centrality, but rather you need to minimize over the elements of the superdifferential of the operator evaluated as 0. Okay, so this means that there are different centrality measures depending on on the vector x that is where we are evaluating the operator. So it may be the case, if you think about production network, that there are shock configuration under which my sector of the economy is particularly central in determining the equilibrium. There are other shock configurations under which a different sector is extremely central, and I have a very limited role. So still eigenvector centrality playing a role, but now you have a multiplicity of eigenvector centrality, and we are telling you how this multiplicity resolved. Is resolved through this minimization over the set of possible eigenvector centrality of the operator evaluated at 0. So this is sort of picking the one that makes this evaluation as lowest as possible. Okay, and you have a sort of exactly analogous result for the convex case, where you get the maximum over the eigenvector centrality associated to the superdifferential of the operator the subdifferential of the operator at 0. Okay, so this is the second result. In the paper, both of them are obtained sort of with a core result. I'm not going to give the proof sketch for this. I would rather spend the last 24 minutes talking a little bit about two of the applications that I selected for this talk. Revisit all the applications that I mentioned in the first slide. So there are different sections for all of them, but let me start with the one on endogenous network games. So this is a situation in which there are n agents playing a complementary effort game. And the twist is that compared to the standard case that has been considered in the literature, we follow more recent development, allowing for an endogenous network selection. So they are chasing both the effort of this agent, but also the kind of connection to make. And the payoff of agent I, given their effort level A and a network W, is of the following structure. Agent I is paying some cost of effort, that's the convex term on the right, so it's costly to exert effort, but there are benefits of effort. These benefits depend on sort of xi, there is their natural proportion to work, the natural skill, but also on what others are doing. So this is a complementarity part of the game. I like to exert more effort if people around me are exerting more effort, and I'm weighting them accordingly to the network W, to the level of connection W. And xi here is the intrinsic ability of I. Now, this is the utility for a given action and a given network. Agent can choose their weighted links, so they can choose who to link with, and we'll allow them to choose them at a cost. So there may be configuration that come free. So for example, there are set of agents I can link with without incurring any cost. But there are some people that are less naturally connected with me, so they have more significant cost. And there may be people that are completely unfeasible for me. So we are allowing for the possibility that linking to some agent is completely impossible and the cost is infinite. Now, with this, the agent is maximizing twice. It's maximizing both with respect to the action that they are taking and to the sort of connection that they are making. With the following payoff structure, there is the utility of a given action in a linear network, and then there is the cost that is paid. And importantly, we are following Sadler and Golub in having the cost being multiplied by the effort. So the idea is that if I'm not exerting effort, basically who I'm linking with is sort of almost cheap talks. We don't do anything together. I'm not paying a cost for making this connection. Connection are really hard to do if we have to do something together. So if I'm literally putting some effort in the task that is under consideration. So this is the complete payoff function, the baseline for A and WI, and then the cost that is multiplied by the effort level of the agent. Okay. Now you do a little bit of manipulation, and you get that the equilibrium of this game, in particular the profile of actions of the players in this game, is characterized by the following fixed point equation. What is done by the agent, or the endogenous variable for the agent I, is equal to a convex combination between their intrinsic ability. Okay, so that's the sort of what they would the sort of propension to work, plus a convex combination of what is done by others. But now the convex combination is taken with respect to the matrix, sort of on here, more precisely, the probability vector that maximize my benefit of connection net of the cost of choosing that particular network configuration. Okay? So that's the fixed point equation that you get characterizing the equilibrium. And it's immediate to see that it's a particular case of our fixed point equation. So you have x beta equal to convex combination of the exogenous vector of parameter plus this nonlinear operator. This is nonlinear because you have a maximum, but is an operator that nevertheless is normalized, monotone, translation invariant. And with sort of weak simple assumption on the cost is also as the property of regularity under natural assumption on C. Notice that you obtain the particular linear case if the cost is 0 for one particular network configuration and infinite for everything else. That's the linear case in which the maximum basically disappears, the cost disappears, and you have the linear specification. Okay? Now, what we do is to solve for this in the case of high coordination motifs, in which I mostly want to match what my peers are doing rather than my own idiosyncratic ability. And let me denote as WC the network that have zero cost, so the sort of cheapest network. What we get is that the limit equilibrium action is equal to the maximum of the eigenvector centrality associated to this cheapest network of the product of gamma x. This is an immediate consequence of our second theorem, actually to the convex version of our second theorem, in which we consider the convex specification rather than the concave one. And the implication is that the most central agent in the network are the one that are at the same time cheaper to link with, but also sort of have higher entry of x. So there is a natural reconfiguration of the network that selects the eigenvector centrality associated to the network that boosts the evaluation of this vector of exogenous parameter. Now, okay, this is in a sense, we think that this is a really interesting sort of, we are taking a classical sort of complementary games on network with allowing for endogenous network selection and solving for the game. But we sort of think this is also particularly useful because it allows us to do optimal targeting exercises. So to extend, for example, the optimal targeting model of Galeotti, Golub, and Goyal to this setting with endogenous network. What do we do? Well, that paper basically solved the problem of optimal targeting in this model with a fixed network W, among other things. So what we are doing is to solve this optimal targeting problem in the case of endogenous network selection. And sort of the target for the designer, as in their paper, is that we want to maximize the equilibrium payoff of the agent given x and beta. And the idea is that designer has the possibility of making an intervention. Rather than starting from the vector of exogenous productivity or sort of exogenous willingness to work x, it can be boosted and moved to some x hat. Okay? But there is a constraint. We follow a sort of constraint how much you can move in Euclidean distance from the baseline level of productivity of the agent that cannot be more than c. The problem for the planner is to maximize the utility of the intervention evaluated in the limit. So let me be clear about what we are doing and what we are not doing comparing the previous paper. So we are more special in that we are focusing for this solution to the cases beta goes to 1, whereas Galeotti, Golub, and Goyal consider the general beta case, but at the same time we are allowing for an endogenous network selection. So it's sort of introducing the innovation, but solving for the high coordination limit and given our sort of rate of convergence result for high level of coordination rather than the full spectrum of coordination motives. And the result about the optimal targeting that leverages the formula that we established in the previous slide is that the intervention that solves the problem 1 must solve the following problem. Maximize with respect to the possible intervention, subject to the constraint, the product between the eigenvector centrality, the maximal eigenvector centrality, and x. So this is just the first line, a rewriting of what we had before. I'm just plugging in, instead of I'm plugging in the value of the game, that is the product of eigenvector centrality time x, because we know that is going to be the limit effort of the agent. Moreover, and more importantly, we get that the pair that solve this problem, the pair of x star intervention and gamma star eigenvector centrality that is endogenously going to be chosen by the agent after the intervention, is that x star is equal to the baseline vector of productivity plus a distortion introduced by the planner that is proportional to this eigenvector centrality, where the eigenvector centrality is the solution of this problem in which you are trying to boost the performance of the agent, but also benefiting from having something that has a larger Euclidean norm. Let me sort of give a little bit of intuition for this result rather than sort of abstract formula in the case in which we were starting from x hat equal to a constant vector. Everyone was equal. So we were all equal before the intervention. We had different network connection, but we were equal in terms of productivity. Then what is done by the decision maker is basically to choose the eigenvector centrality that maximizes the Euclidean norm of the eigenvector centrality. So maximizing the Euclidean norm is equivalent to sort of having a very dispersed. So if it was a variable, you would, if it was in the set gamma c, you would like to boost a single agent with all your budget. Okay, that would be the ideal thing that you would like to do. And the reason why you get this, that is sort of insight that is not present without the endogenous network reconfiguration, is that you want to leverage the endogenous network part. So you want to make concentrated intervention compared to the case with an exogenous network, because after the intervention, players are endogenously going to choose network that make this single intervention that you made more central. So you have a natural force towards making concentrated intervention, because then the network is going to reconfigure towards that. Of course, if the level of productivity of all the agents to begin with was not the same, you have the trade-off of wanting to boost agents that are already central so that you reconfigure towards them, and having a concentrated intervention. So the problem is not necessarily bang bang in the way in which I described before. But that's sort of an immediate payoff. I mean, after just some work of our characterization of the fixed point for the nonlinear case. Okay. So if there are questions about this application, happy to take them here. Otherwise, I'm going to move for the last 10 minutes to a second application that we have in the paper.
Can I actually ask something? Can you remind me, gamma C is the set of networks that cost at most C?
No, that costs 0. Okay.
That costs 0. Okay. Okay. So great. So that was going to bring my next question, which is, so is that saying that, and maybe that was already in the existing papers that I should know better. Are you saying that in every equilibrium, the people choose a network that is free?
No, that in the limit.
In the limit, yeah, in the limit.
In the limit, they are going to focus on the one that have bounded. So the cost as beta goes to 1, basically they are restricting to costs that are arbitrary.
Going to 0. Okay.
Going to 0. Okay. Yes. And the lower semi-continuity is getting you that then you can focus on 0. Okay. Yes. So in the limit, the key role is playing by the free connections. The one that, I mean, for some models are basically all the connections. So the classical setting that is considered here is you have cost 0 or infinity. We are being more general, but so you think about the fact that you can choose every free agent, free neighbors configuration. You are limited to 3, but you can choose all of them. So that's sort of one classical, and you have cost 0 for them and infinity for everyone else. Okay, we are allowing for something more to cover more application, but the result is that this something more is not that important in the limit as beta goes to 1. For the result that we have on the sort of Bonacci centrality, they play a role. Okay, and then we're exploring that more in detail. But as beta goes to 1, basically this sort of either free or unfeasible, basically all that matters. Okay. Good. Now let me move to a second application, the one to financial networks. So there we consider an equilibrium model of systemic risk evaluation, where there is a group of financial institutions that are exposed both to idiosyncratic losses and all cross-capital interdependence. So in particular, there is a set of banks, K, and there are a set of state of the world. Both of them are finite, and you should interpret the state of the world as macroeconomic scenarios. And each bank has a particular idiosyncratic loss that they are exposed to in state omega. Okay, so X, K, omega is the loss of financial institution K in state omega. And we follow the setting of Adrian and Brunenheimer in endowing each bank with a core set of scenarios. Okay, so every bank is not considering the full post range of scenario, but a core subset that is basically the set that is relevant for them oftentimes. And they evaluate the risk in each of these scenarios using a conditional risk measure. So a risk measure that evaluates the exposure conditional on being in this scenario. And there is a financial network that is represented by a strongly connected stochastic matrix M that is telling us what are the banks that are interconnected with the other banks. Okay, so that's the setting. I mean, that's sort of the bank interconnectedness and their sort of scenario. And what they do is to produce an evaluation of the expected total loss in each of these considered scenarios. Okay, they have to do this scenario evaluation of their losses. But their losses are a combination of their exposure to the idiosyncratic real economy risk, and a combination of their exposure to the other banks and the losses of the other banks in those states. This is the financial interconnectedness. The return is the percentage return that I obtain is a convex combination of my percentage return on the return on percentage loss on the real economy asset plus my exposure. Now, notice that the exposure of the other banks is still a random variable from the point of view of bank K, because the scenarios that the different banks are considering are in general different. So the partition are different, and the losses of the other bank are only measurable with respect to their own scenarios, so what they declare, not with respect to the scenario of my bank. And again, following Adrian and Brunenheimer, we consider the case in which each bank uses a conditional risk measure. So they don't evaluate their exposure at the expected value, but following standard regulation, use a conditional risk measure. The conditional risk measure can be sort of described in the following way. A conditional risk measure is always the following form. So I'm evaluating the profile of loss, L, and I'm considering a worst case scenario. So I'm maximizing these losses with respect to probability measure, but this maximization is not unconstrained. Are scenarios, there are probability measures that are more realistic, in the sense that the cost for them of using them is very low, and some of them that are unrealistic for the central bank, and therefore that have a very high cost. And the conditional risk measure trades between this sort of desire for robustness and the fact that some scenarios, some probability measures are more realistic than others. So the evaluation of one bank in state omega of their profile of losses is this maximization with respect of the conditional risk measure that has the requirement of being supported only on the states that the bank still believes possible. Now, if banks are evaluating their losses in this way, what you get after some manipulation is that the equilibrium evaluation of each bank as a function of beta and of the state in which they are is their conditional risk measure applied to what? Well, applied to their exposure to the real economy and what is declared by other bank as their expected loss. Okay, so this is a fixed point equation that you end up doing when banks don't evaluate it at the expected value, but using this conditional risk measure. Okay, and when we look at the limit as beta goes to 1, what we get is we are looking at is the case in which the losses from financial interdependencies dominate idiosyncratic losses, the highly financial economy in which most of my exposure come from the financial sector and across bank interdependency rather than from exposure to my own idiosyncratic losses. And we immediately get, because of the concavity of risk measure, that is a property that is assumed for risk measure, that the limit exists and is independent of the state and bank's identity and have the formula that is given by our second theorem. It's basically the minimum over the eigenvector centrality associated to this nonlinear operator. Now, the sharper conclusion that you get here, however, is the one that you obtain in the case for smooth risk measure. Okay? So I want to focus on that. Smooth risk measure are risk measure where the cost of the evaluation has a particular attractor. The cost is equal to, sorry, this should be a maximization of a scenario of the losses, and the cost is some divergence measure from a benchmark probability scenario. Okay? So you have a benchmark probability scenario, and think about considering relative entropy deviation from this benchmark scenario. And so you want to consider something that maximizes your losses, but it is not too far away with respect to relative entropy or other divergence measure from this benchmark probability measure that you are using. Well, what we obtain in that case is that basically in this case of smooth risk measure, in the limit as beta goes to 1, so in the highly financial limit, basically all the sort of robustness that is introduced by evaluating rather than an expected value with this probability P0 using a conditional risk measure is killed by the coordination motives in the limit. The limit as x beta as beta goes to 1 corresponds exactly to what banks would declare as their evaluation if they were evaluated losses at the expected value. So it's the product of the expected evaluation of the losses pre-multiplied by the eigenvector centrality of the matrix of connection. Of course, sort of the equilibrium losses are going to be determined more by banks that are more central in the economy. But all sort of the precautionary motives that are introduced by the use of conditional risk measure, you wash away in the high coordination motive. So it's killed by the coordination motives of the bank, and this can happen even sort of in the case in which the robustness concern of the different bank was different, even in the case in which they were using relative entropy versus different divergence measure. Importantly, this is not the case for all risk measure. If you consider value at risk, for example, it's still covered by a previous result. It's still sort of, expected shortfall. Expected shortfall is covered by our previous result, so you can compute the equilibrium, but it's concave and non-differentiable. So what you get is that you don't collapse to an expected value evaluation, but rather the use of this conditional risk measure, even in the limit of a highly financial economy, produces robustness in the evaluation and sort of a more cautious evaluation of running out of time, so I'm just putting up the conclusion slide that basically tells what is done in the rest in the rest of the paper. We do more application. Considering production network, the limit of opinion of non-Bayesian learning on network, a formula for the value of zero-sum stochastic game with a continuum of action, high patience limit of recursive preferences. All of these are applications that again are obtained as immediate corollaries of our main theory, main results. And we also do more theory. Coming back to Agathe's question, we give a linear rate of convergence to evaluate the fitness of approximation. We go beyond the concave case to give a formula that can be applied to the zero-sum stochastic game application. And we have a Bonacic-like formula for the fixed point away from the limit as beta goes to 1. And I conclude here. Thank you very much for your attention.
Okay, thank you very much, Giacomo. We have, I'm going to give priority to Agathe and Sanjeev if they have comments. We also have at least an intervention by Ilya in the chat, which either he's going to ask or I'm going to read to you later on. So Agathe, Sanjeev, if one of you wants to go first and make some further comments, questions, otherwise we'll move on.
Can I start? I'm sorry, I joined late, Giacomo.
Yeah, no.
My apologies. I'm aware Agathe asked a few questions, so I'm jumping in just to appear not to, be completely lazy. So let me just say that I finished teaching, and then there's some stuff, so I apologize. I finished teaching a little after 4. So, okay. So I missed about, I think, 15 minutes of your talk. So let me just for concreteness, and I'm aware there is limited time. So if you were to go to, yeah, because you presented two applications. One was the games, games, yeah, endogenous network games. And then you presented also an application to interventions in networks. So I think the question I have is probably common to both of them. Um, and basically, I was trying to get a sense of what are your thoughts if the way I see it, this payoff function is sort of assuming that the actions are strategic complements. And also, I think in the second application on interventions, my understanding is that you're looking at the complements case. No?
Yes.
Yeah.
That's it.
So I've just had a kind of a high level question, because right. I mean, basically the substitutes case has been studied in the literature, quite a lot. And I wondered if you had any thoughts on that.
Absolutely. So this is a real restriction. So we cannot do the substitute case. That is coming from monotonicity. So monotonicity, the assumption of monotonicity of the operator that gives us a lot of mileage and allow us to prove our results is basically one-to-one here with the complementarity assumption. And I want to emphasize that this is the particular application, the one of game on network, where monotonicity is not obvious as the one thing that you want to consider, because substitution has been considered a lot. Indeed, what I try to emphasize is when I was introducing that. So we are covering the case of complements. Luckily for us, in all the other application, this monotonicity is the only relevant case, in the sense that in production networks, I'm trying to give sort of a high-level response, okay? For the specific application, I agree there are two cases that are important, and there is also a mixed case that is important. We are able to cover only the complementarities one, because we need monotonicity. In production network, basically, the price that is charged by a firm is a monotone positive function of what is charged by the other firms, because it's taken as an input. So this monotonicity comes for free. In financial networks, that is the application that I discuss, given that you are exposed to the losses of the other banks, as long as we don't allow for short selling, that sort of, or something like that, you have monotonicity. That is the case that is usually considered in the literature. I mean, as far as I'm aware, is the only case that is considered. In non-Bayesian opinion aggregation, we are basically restricting to what I would say is 95% of the model, in which I'm not negatively reacting to what you are saying. So if you increase your opinion, this is at most have a neutral effect on me, but I'm not going to decrease as a response my opinion. And in a sort of control Markov decision problem and Bellman and dynamic programming, monotonicity is for free. The games on network with complementaries is the application in which monotonicity required to subspecialize to complementarity rather than substitution. But we can, at the moment, I don't honestly have an idea about how to do without monotonicity. It's one of the two key assumptions. While normalization is not important, monotonicity and translation invariance are very much key.
Okay. Sanjeev, shall I pass the ball to Agathe?
Please.
Okay.
I have a perhaps ill-defined question, and maybe you answered it, and I'm just going to reveal my lack of understanding. But so in the linear case, we know, and if you take, we know in general, but in the limit, we know that you can characterize the solution by a particular eigenvector, and you're kind of showing that in the nonlinear case, you can do that as well. But they're not the same eigenvectors, correct?
No, they are not the same in the sense that, okay, so if you apply this result to the linear case, this is the same eigenvector.
Yeah.
Because the Jacobian is the matrix itself, right? For a linear
Yeah.
operator, the Jacobian is basically the operator. So
Okay,
the
because I was
Jacob-
going to ask, like, do you have a sense as to, like, I agree in general they're not the same, but and if you assume that T is linear, it is the same, obviously. But are there other cases where like they would actually coincide, and in some sense, the linear model is give
So
the
I
same
would say
prediction
that-
in the limit, or yeah?
I would say that is the message of the continuously differentiable case. The continuously differentiable case, the one covered by the first theorem, basically it's behaving as if you assume from the beginning that
it's
the
linear.
operator is linear with what matrix W? In principle, we don't know which one. The matrix that is the Jacobian of the operator or T at 0. So suppose that you started with the linear model with JT0 being W, you get exactly the same. Now,
Okay.
this is not the case in the concave case, because in the concave case, if you start with one of these matrices, depending on the x, for some x, yes, of course, you're replicating that. But for a different x, you would need to use another operator. So this is the fact that the limit operator is not collapsing to a linear operator. Whereas here, in the continuously differentiable, even if the operator itself of T is not linear, the limit operator is a linear operator, is the inner product of the eigenvector centrality times x.
I
So
see.
that's
I see.
that's the strong message of the differentiable case.
Okay.
That for the differentiable case, in the case in which I have high coordination motives, basically to a good approximation, you can focus on the linear case corresponding to the Jacobian of the operator at 0. That's not the case when you have non-differentiability of the operator, for example, for endogenous network selection. There you have to be much more nuanced and consider different eigenvector centrality depending on the vector that you're considering.
I see. Okay. So non-linearities are okay in the limit. Non-differentiabilities are not okay in some sense. Okay.
Yes,
Or like
exactly.
Perfect. Thanks.
So Agathe, do you have anything else, Sanjeev? Otherwise, I'm gonna open the floor.
So let me make one very quick high-level remark. Okay. So, and I apologize, I missed the first 15 minutes. So this may actually, you must have covered, you probably discussed this. But so if you look at the early papers, by different folks who've been working in this field,
Yes.
Ballister, Calvo-Zenu, etc. And there was always a concern about nonlinearities. And
Yes.
always a concern that this is the functional forms, and this is very special. And we need to go beyond that, and we need to ask how it moves. And I think the sense was that, I mean, the sense I picked up from talking with these folks and was that two kinds of responses. One, that you would probably lose this elegance of the matrix algebra and the monatic centrality stuff. But if you had enough smoothness in the problem, that somehow you would probably, there would be a sense in which the outcomes in this nonlinear thing, as long as somehow the nonlinearity was reasonable, would still somehow be similar to what the ideas were. Now, I appreciate that this is a contentious sort of issue, but a high-level remark is that, let's say, eigenvector centrality and monatic centrality and maybe other centralities, are somehow highly correlated in many networks. Okay, so let me put the question to you. So, because I missed a lot of what you were going to say, would you say that, because a key sort of argument in this literature on games on networks especially has been that this way of thinking identifies a particular centrality measure, and it prioritizes that and identifies it relative to other centrality measures. But that's not the feel I'm getting from your result, because you have these other centrality measures coming out, eigenvector centrality, and there is some Bonacci-like result. So I was not sure, again, this is very high level, how I should take your paper, in the context of that sort of discussion.
Okay, good. So it's, in a sense, it's reaffirming, even beyond the linear specification, the role of eigenvector centrality. So you still sort of need to it's telling you in this kind of models, especially if you look at the limit as beta goes to 1, in which you have a high coordination motive, eigenvector centrality is sort of still the way in which you go from a network to the sufficient statistic that is sort of telling who is more central. Now, what you may lose, and sort of you lose it in the case of endogenous network, we have something about different payoff forms rather than different endogenous network. But let's focus on endogenous network. What you lose is the existence of unique matrix W that then is associated with a unique eigenvector centrality. So you always care about an eigenvector centrality. But now the endogeneity of the network, for example, is telling you, okay, but there are multiple networks. For each of them, the important thing is the eigenvector centrality. So this is not obvious ex ante. And then it's telling you, okay, while you go and find what is the eigenvector centrality that is relevant, well, go among these networks to look to all the set of this network, their eigenvector centrality, evaluate how they sort of map into a product gamma X. Look at the one that maximizes, that's the right eigenvector centrality. So there are many eigenvector centrality because there are many networks. Which one you pick? The one that maximizes this product gamma X. So it's telling you where to go to compute an eigenvector centrality. So reaffirming role of eigenvector centrality, but since there is a multiplicity, also selecting which one is the right one to compute the equilibrium. And we care very much about also the other possibility of considering more different payoff structure rather than just endogenous network. And this is, for example, what we explore a lot in the general equilibrium production network application, because there is a very natural candidate, a very influential class of different payoff structure, if you want, counterpart of different payoff structure that has been studied a lot, that are these nested CS production functions. So we go and look at what happens if you can't change not just the network selection, but also the specific payoff structure.
Thank you.
You're welcome.
Okay. So I don't know whether Ilya wants to talk and ask his question explicitly, otherwise I can read it.
Oh, okay. I can also try to read it, okay?
Sorry, we can finish the official part because it's
yes,
time, I guess.
Yes. It is 4 past now, actually 2 minutes after that.